the introduction. In the beginning, I want to say thanks for everyone who is still here to listen to today's last presentation. And I do hope that this presentation can benefit you a little bit. In this presentation, I will talk about how to use the wind turbine noise to emit the subsurface structure. And at the beginning, I want to say this is the new method, and it combines of two steps. In the first step, we'll use the wind turbine noise to retrieve the reflected body wave. We get both the P wave and S wave. And you can see there are lots of periodic signal here. They are the free surface multiple. So we further propose the inversion-based seismic interferometry to remove this multiple and to invert the primary reflected response to help to figure out the subsurface structures. Both these two steps is very interesting and very challenging. And now we will focus on the first step. Okay, and Yanni just said that the basic idea of seismic interferometry is to use the cross or autocorrelation to turn this ambient noise into the signals. And this initial idea is proposed almost 70 years ago by Arke and Clapper. Then there is some theory derivation given by someone, and this method is developed from the primary wave to the coda wave interferometry. And there's lots of applications for this, like image-craft or monitor the subsurface value change over time. And in this year, Elita, me, and Jizhong, we write a paper to detailedly talk about the artifacts, the orientation of the artifacts for the coda wave. Although there are lots of successful examples for the surface wave interferometry, while there's still lots of challenging and confusing problems for the coda wave interferometry. So in this presentation, we will figure out how and why we can retrieve the body wave, and further how to remove the multiple in this body wave. Okay, Cyan, Alexa, Alejandro had talked a lot about this figure, and they use the traffic noises. For me, I focus on the wind turbine noise here. And you can see the geophone is located at the center of this wind turbine, and it's a three-component geophone. So we have the Z, N, and E components. The recording time is 15 months. And because this geophone is far away from the traffic noise, so the domain identity we recorded is just the wind turbine noise. If you compare the net energy of the noise with the wind speed, you can see the clear coherent with each other. So this, to some extent, verify the source of these noises. And now let's look at what the noise looks like. This is one typical day's noise. And if you do the autocorrelation average the half hour, you can get a single trees here. So for this one type of day, we get 48 trees here, and this figure shows the all 15 months autocorrelation results. I will first give the answer what we get by this autocorrelation, and then explain why we can get that. By the Z component autocorrelation, we get a reflected P wave here. We also do the autocorrelation for the N and E, the horizontal components. And they adjust the reflected S wave. These two components look similar, and if you compare the P and S wave, you can see the periodical or the time delay is different. This is just because the velocity for the P wave and S wave is different, even they are the same wave path. Then how can we verify we retrieve the body wave? We verify that by the simulation data. This is the local geology map of the wind farm, and there's a free surface. There is also a high contrast impedance interface, which is the basement. The depth of the basement is around 100 meters. And so we built this two-layer model. The parameter is averaged from the well-log data. Then using the two-layer model, we do the elliptic forward modeling. This is the vertical component. You can see there's lots of periodical reflective wave here. They are just the multiple reflected between the free surface and the basement. For the vertical component, this is the P wave dominant. We also get the horizontal component. There is also periodic signal, but the velocity difference is the S wave velocity. So this is S wave dominant. Let's see more detail in this short gather. So for this near offset area, and we analyze this just the periodical reflected body wave. So if we go further, we see the surface wave here. Keep going, we see body wave again. This is just because in the near offset area, the body wave is just propagated vertically and reflected back. While for the surface wave, it propagated horizontally. And due to the two different propagation directions, the body wave and the surface wave will not overlap in this near offset area. So this area is body wave dominant. While for the middle or the farther offset, they may be overlapped and challenging to separate each other. Well, this is for the active source. How about the passive source or the ambient noise? We also do the simulation. And this is the geometry of the wind turbine and the geophysics here. Based on this map, we give the near offset area, which is 2 kilometers, consistent with the active source. And refer this distance between the source and receiver. We selected 8 traces, which is in the near offset area. And we convert this selected trace with random numbers and stick them together to simulate the wind turbine noises. Then we do the autocorrelation, which is same with the field data, and we get the similar results with field data here. Then we sticking all these traces together to get the average trace here. So this is the simulated data, remember that? And then we compare the simulated data and the field data. You can see there is a good consistency between the travel time. And if you, this is for the Z component, if you change it to the frequency domain, you can see the same dominant frequency here. Remember, we know the depth of the first layer and we know the velocity for both P and S wave. So we can calculate the theoretical frequency here. It's 6.5 Hertz. It's the same with both the synthetic and the field data. So for now, we verify that this dominant frequency just corresponding to the two-way travel time in this first layer. So this verified that we retrieve the reflected body wave. For the Z component, we get P. And there's similar situation for the S wave. And because the velocity is decreased for S wave, so the dominant frequency is also decreased from 6.5 to 2.5. Okay, for now, we verified that we can retrieve the body wave, and we know this periodic signal are just the multiples. So how can we remove this multiple? Next, we will focus on the second step to see how can we remove this multiple and figure out the subsurface structures. The basement is coming from the receive process theory. This theory is just established the combination between the physical wave state and the ideal wave state. Here, the physical just means the realistic situation, and there is a free surface, there is a primary reflected wave and multiples. The ideal means what we expounded. We do not want the surface multiple or the multiples. So we remove the free surface. We only want the primary reflected wave. For our case, there is a wind turbine and there's free surface. This wind turbine continues generate sources and it propagates to this subsurface, interact with the material, and reflect back from the outgoing wave field. This outgoing wave field will reflect back again to form the multiples. While for the ideal wave state, the free surface is removed. The source is that function, and the outgoing wave field is a primary reflected wave. So if we take all this wave field into this theory, and after derivation, we get the transformation relationship between the field data, the for the physical state and the ideal data for the ideal wave state. The physical meaning of this equation is really easy to understand. It just means if you convert the downgoing wave field with the primary reflected wave, you will get the outgoing wave field. So for now, we build the forward model equation here. Based on this equation, we established the objective function to minimum the data residual between the selected and between the synthetic and the observed data, which is all same with the traditional observation methods. And because the subsurface layer is limited, so we add a sparse constraint regularization here. So what we get by this inversion? This is the input data, and there is a free surface. So this is all the multiples. This will pass. This is what we get by inversion. Compare with each other. You can see this multiple has been removed. And for the P wave, we get two subsurface layer here, interface here. And this is the wave path for the primary reflected wave. For S wave, we only get one interface. That's maybe because the reflected coefficient for the second layer is not is too weak. Maybe all the recording time is not long enough. So for now, we know the wave path for the primary wave, and we know the corresponding travel time for the shallow layer and for the shallow interface and deep interface. So this just gives us more confidence to do the subsurface property analysis. So next we will compare the peak amplitude change for both P wave and S wave for the first layer, which is associated with attenuation. Attenuation affects the peak amplitude. And for the deep layer, because the travel time is much longer, and the cumulative time shift will be more stable. So we will use this layer to analyze the time shift. So it indicates the velocity change. This is the results. And the blue line is the peak amplitude for the P wave, and these two is the peak amplitude for the S wave. They are just the two different horizontal components. And there are two obvious characteristics here. First, you can see the amplitude change for P wave and S wave is in opposite direction. When this increase, they decrease, increase, decrease, increase, decrease. And another characteristic is that there is a seasonal change, or the periodical change just appear again and again. Well, for the time shift, there is also periodical character, but the periodic is different. This is for the time shift, and this is for peak amplitude. So the velocity change is different from attenuation. And Cyan and Alejandro Exa had analyzed a lot about what will affect this. The initial conclusion is that the amplitude is more sensitive to the groundwater level, while for the time shift is more sensitive to the temperature. And one more thing I want to say, based on the wildlife velocity, we calculate the depth for the second layer. It's can up to 1.2 kilometers. So this is not only about the near surface, it touches the area of the seismic exploration. And the background detail over T can up to 1%. Okay, last I will give the conclusion that we verify that the subsurface structures can be imaged using the wind turbine noises. And the autocorrelation with different component noise can contrast the reflected P and S wave. The inversion-based interferometry of the convolution can further invert the primary reflected wave to help to figure out the subsurface structures. And one more thing in the future work. So we have to do some work to use autocorrelation with the cross components, like you autocorrelate with the N component with E or with N. There is also lots of interesting phenomenon, and later do some theory analysis for that. So if you want to see the future work, come here again next year. Yeah, and so the depth can up to more than 1 kilometer. So there may be a potential to apply the two-step method to the CCS because it's money saving, right? We don't need to spend a lot of money to do that. Okay, this all. Thank you.
Thank you for the great advertisement. Questions from the students first? If not, it's gonna go to.
Well, see, I'm emeritus, I'm like third order on the pecking order of questions. But this is kind of a unique area in the sense that was alluded to by the BP folks as well. That you really have some old shales and things right up at the surface. And what's piled up on top are these tills, these glacial tills. You get a big reflection on there. So it's no surprise that you're seeing a heavy duty reverb on there. And it's really cool that you could remove it. But that's not everything. So if you're down in Houston or somewhere else, you're gonna have different challenges doing this type of thing.
Yeah, the assumption here is that you need to have the source in the near outside area, and there should be a strong interface. Subsurface.
Yeah, which we do have here.
Yeah.
So.
Other questions? Not, thank you, Feng, for the last.